Hi, my name is Eckhard Ohlmer. I am one of the product architects for an ICE software-defined radio product line. In our previous video, RFNoC in 10 minutes, we gave an overview about how the USRP FPGA functionality can be modified using the RFNoC framework. In this video, we'll demonstrate that workflow by extending a standard FPGA design that comes with USRP X410 with custom OFDM modulation functionality. We outlined the two variants of how to get from a set of FPGA IP blocks to a bit file and deploy it in our previous video RFNoC in 10 minutes. In this video, we focus on the text and command line based variant shown on the right hand side. We assume that the UHD driver, Xilinx Vivado have already properly been installed as outlined in the UHD manual. First, we'll explain the key file that describes the FPGA design, the so-called image core YAML file. Then we'll show how to instantiate an additional FPGA IP block in there. We'll show how to compile an FPGA bit file. And finally, we deploy that bit file to USRP X410 and validate that the new FPGA IP block has been properly included. The agenda item number 1 is covered in this video, and item number 2 and 4 are covered in a companion video. Let's start from a standard design for USRP X410 that is provided by an I. This FPGA design provides access to 200 MHz of RF bandwidth, and the FPGA image for that design can be obtained from an I through the UHD image downloader tool. The design has 2 radio blocks covering 2 radio channels each. Each radio block is connected to a dual channel sample rate up or down conversion block, and those are connected to 4 stream endpoints. The 4 streams are communicated between FPGA and host through 4 10 gigabit Ethernet links. Our goal is to statically add OFDM modulation, so FFT and cyclic prefix handling, right after the sample rate conversion blocks, where the green box is. So the target FPGA design would look like this. We have added dual channel FFT and cyclic prefix removal into both receive path and dual channel IFFT and cyclic prefix addition into both transmit path. The static design on the previous slide does not provide a lot of flexibility in terms of data routing. The FFT processing is always statically added into the data path. This is FPGA resource efficient as only 4 stream endpoints and a relatively small crossbar are utilized. Especially in the beginning of a design phase, users may want more flexibility to bring up new functionality in steps. This can be accomplished by adding the FFT blocks with streaming endpoints connected to the crossbar. Now, users could switch between the standard functionality of the image, sending data from the host to the FFT block and back to get familiar with the block, and routing the transmit or receive data through an FFT similar to the static design. Both the static and dynamic design use the same principles in the image core YAML file, so we'll explain the static design in this video, but provide the YAML files for the static and the dynamic design. To create custom bit files, you'll need to clone the UHD repository to your computer. The image core YAML files that we can either compile directly or use as a starting point for customization, they can be found in the clone repository. So let's have a look into the clone repository and navigate to the FPGA folder first. USRP X410 is a 3rd generation USRP, so let's open that folder, navigate to top level designs, and there you can see the different 3rd generation USRP types in there. We'll open the X400 folder, and the design that we want to modify is located in here, as well as other standard shipping designs. So let's open the image core YAML file we're interested in and explore its contents. A truncated preview version of the image core YAML file that we just opened is shown on the left, and the corresponding block diagram is shown on the right. The image core YAML file contains 6 sections that are highlighted in different colors. The general parameters section configures parameters such as USRP type and the RF bandwidth. The transport adapter section is a reference to another file, and this file defines how the USRP can be interfaced with, for example, from the UHD host. The stream endpoints sections lists all the stream endpoints that can be used to reconnect RFNoC components dynamically at runtime from the UHD host. The NoC block section instantiates the different FPGA IP blocks in the FPGA design. The connections section defines all static connections between NoC blocks, and these connections, they cannot be changed on runtime. Finally, in the clock domain section, all required FPGA clock sources are connected to the different NoC blocks. Now, let's have a closer look into each of these sections. We'll start with the general parameters section and go through its parameters. Be aware that these parameters may vary depending on the USRP type. The cheddar width parameter determines the width of the cheddar bus that connects the different NoC blocks and impacts the maximum data rate that can be transported over that bus. This parameter typically has to be increased as we increase the RF bandwidth. The device parameter specifies the device type, in that case it's USRP X410, and the board support package is automatically selected based on that parameter. The default target parameter is used by the RFNoC image builder tool to potentially differentiate between variants of the same USRP device type. It has a static value, X410, for X410 devices. On other devices, such as USRP's N300 or X300, it's used to differentiate between the different transport adapter variants. The inherited X410 radio base YAML file instantiates and connects two channel radio blocks that are commonly used across all the X410 image cores. The inherited X4XX base YAML file instantiates a specific transport adapter. In our example, that's 4 10 gigabit Ethernet links. For non-USRP X400 devices, the transport adapter would not be instantiated through such YAML file. Rather, the default target parameter would be used for that purpose. The RF bandwidth parameter determines the maximum usable RF bandwidth, and viable options for that are defined in the board support package. The remaining parameters that you can see here determine how onboard DRAM resources are exposed into the RFNoC image core. Next, let's have a look at the list of streaming endpoints. We got 8 streaming endpoints in the design. The first 4 will be used to connect the DUCs and the DDCs to the host. The last 4 allow to connect to a 4-port replay block, also from the host, that is part of this design. Each of the streaming endpoints requires a unique name. In this case, that's EP0 up to EP7. The control and the data port parameters determine whether or not the stream endpoint processes control and data cheddar packets respectively. And as of UHD 4.9, only the first stream endpoint, EP0, can process control data. The buffer size parameter determines the input buffer size of the stream endpoint, and this buffer is for data flowing from the cheddar crossbar into the stream endpoint. The first 4 stream endpoints have larger buffer sizes assigned, as they are used to receive data from the host, and that operation can be subject to jitter and bursty traffic, and that could lead to overflowing or underflowing the radio. The remaining 4 stream endpoints have smaller buffer sizes assigned, and those are not connected to the radio but to the replay block, and the replay block can cope with host to USRP jitter. In the NoC block section, we instantiate all the NoC blocks that shall be part of our design. So for standard bit files, these are DUC, DDC, and the replay block typically. Each NoC block instance needs to be assigned a unique name. The NoC block interface is captured in a block description file that needs to be referenced here. This block description file defines user modifiable compile time configuration parameters and the default values, required clock signals, and data input and output ports. Compile time parameters for that block can be modified in the parameters section. In this example, we instantiate a 2-port DUC, whereas the default value would be a single-port DUC. In the connections section, we define the static connections between the different NoC blocks. Each line represents a unidirectional connection between 2 NoC blocks. Source block and destination block names reference the unique block instance names defined in the NoC block section. We also need to define the data port names and add an index suffix to input or output ports for blocks that are configured to have multiple ports. The 4 lines in our examples connect the first transmit and the receive channel. That is the radio to the DDC and the DDC to the stream endpoint in the receive direction. And for the transmit direction, we connect the stream endpoint to the DUC and the DUC to the radio block. Finally, we connect the required clock signals to NOC blocks that need clock signals other than the RFNoC chatter and control clocks that are connected to each NOC block by default. The available clock sources are defined in the board support package for the USRP device type. The clock inputs required by each NOC block can be found in the block description file. In our example, the first line connects the compute engine clock to the DUC, and in the second line, we connect the same clock to the DDC. So where are we in the workflow of creating a custom FPGA design with RFNoC? In the first part of this video, we introduced the structure and the parameters of the image core YAML file that defines our FPGA design. In part 2, we will modify the standard shipping FPGA design and add OFDM modulation and demodulation functionality on the FPGA. See you in part 2.